very pleased to be here, and I'm very honored to have the chance to share thoughts about catalysis and perhaps as part of it to reshape our world. What I'm going to share with you is about what the chairman has introduced. I don't have to repeat this. We are all asked to contribute to this. It's not a matter of, we wait until somebody is doing that and then I will maybe follow on this. This is why I've chosen this title. If you go to a casino, you have the option to diverse, to spend this all over, or you said, okay, I think I have only one shot, or maybe two, all in. So, and what that means is this is another way of showing what we talk, what we say, what we mean if you say it's about sustainability. What are the expectations for the future? If you talk to chemists, and I guess there are some in the audience, but perhaps not all, you ask yourself, okay, chemistry, these are the people who make the world dirty. You have to clean it up. And in fact, it's not true that we make the world dirty. It's the way of using resources to the better world, to the mankind. And there are, of course, mistakes. As in nature in general, we're part of a nature, are mistakes. So it doesn't matter now to complain about, what is, let's go in the future, do something new and reshape. Expectation is this. These are words. But what does it mean? Behind that, I hope to explain that to you more clearly. Greener means that we do use chemicals which are not toxic. So as part of the synthesis is the question how we get rid of this stuff at the end of the lifetime. In wastewater, in all this waste we produce. And in nature, there's no waste. Everything is in a certain way recyclable. And we need to adapt to this more rigorously. The other thing is, you don't want to make thousands of different experiments in order to make a compound. Here's the hour for the theoreticians. You should predict something. The prediction, the value of prediction, which basically is the difference between science and theology, right? So we respect each other, but the job of the scientist is to be predictive and not trial and error. So if you put all this together, you end up with this kind of advertising slide you have seen so many times. So sustainability, and as pointed out very clearly by our chairman, is more than chemistry. It is a bunch of different business and thought aspects under one umbrella. And if you now go to the chemistry part, as is, we have, again, in the chemistry, various different aspects we obey here. And if you talk about green chemistry, the green chemistry is a bunch of rules we might want to obey in order to make synthesis, in order to be producing better. Fortunately, we are not the first one who think about it. Of course not. The question is, who is listening? There are two gentlemen, 20 years ago, they wrote a book, Green Chemistry for the Practical, so practical use. And the definition of green chemistry is sometimes not clear to everyone. It's not making us happy. The green chemistry thing is the design of chemical processes and processes that reduce or eliminate hazardous substances. And so that means it's immediately connected to pharmaceutical, toxicological aspects. So what we inhale, what we drink, what we eat, everything what is on Earth we basically produce will end up in our chain, so to speak. John Warner and Paul Anderson. John Warner is an entrepreneur. He used to be a professor of chemistry in the University of Boston. And Paul Anderson, he's in the US as well, and he is a professor for chemical engineering and various other things. And they wrote this book. And they thought, okay, let's put all the different aspects together which define the green chemistry. These are the 12 principles of green chemistry. And you can start on the 12th and go back, it doesn't matter. They're all interconnected. What that means is, if you want to be really according to this rule, you're trying to make what you do as a chemist accordingly. Pollution prevention means if you do a synthesis, nobody next to you should be a caught because of what you produce, right? Or if you do synthesis, you would like to be atom economic. Even if you produce water at the end of a chemical reaction, that's waste, actually, by definition. So why don't you try to make a reaction more efficient in this way? Cut a long story short, we hear about this. Catalysis is a key thing. What is catalysis? It's a kinetic phenomenon. It's accelerating a chemical reaction, lowering the energy you need in order to activate the process, right? So we're talking about more efficiency in using resources. And there are reactions which would never take place by its own, although thermodynamically easy to undergo, actually, on paper. Let's say N2 and hydrogen to make ammonia, the fertilizer. It will not take place without a catalyst. We would not sit here without this process, right? So which is basically feeding Earth. So therefore, now we go a deeper step in asking ourselves, how could we do this even more efficient? In Berlin, and now I do a little advertisement, I'm sorry about that, but the point is, you will see, it's not that I'm hiring somebody or something. The point is, it's all about education. And we need a common language to do that. It's not enough to publish papers or to go to politicians and say, I need more money. It's all about us. We are the people. If we do not change, if we do not have the same language, we'll fail. So we thought, we had the chance, it all starts to have some funding, right? Of course. The Germans, in 2007, set up an initiative which was called the Excellence Initiative. It's about all disciplines, from astronomy to deep sea diving. Where are the best people trying to interconnect fields and to generate something new? And we had the idea, hey, catalysis is spread over in very different disciplines. In chemistry, homogeneous, heterogeneous catalysis, whatever that means, in biological catalysis. So chemistry and biology, they are not strangers. They're basically the same. Because if you look at the kinetic phenomena, we're running a reaction. So producing ammonia in a bacteria is chemically the same as we go to a plant, chemical industry, BASF, to make ammonia. The difference is the conditions are very different. Yeah? The nitrogenase does the ammonia synthesis at room temperature and 1 atmosphere. The Haber-Bosch process takes 400 centigrade and 50 or 80 bar. Why is that? We said, okay, we should basically understand this. And so we set up this program, which is called Unifying Concepts Catalysis. It's another type of reunification of Germany, I thought. But let me tell you what that means. And we had the joy to do this for quite some time, you see here. And it was about the way chemistry, we as humans do, and mirror this, how biology in cells, this is taking place. And we focused that on activation of methane, activation of carbon oxides, monoxide, dioxide, these are key carbon-1 sources, and activation of hydrogen, oxygen, and water, and hydrogen peroxide, because this is something which, blue planet. That's what we are. And then another thing which is basically very complex is how reactions are triggered over a long time and space chain in nature, and we might be able to learn this, to take it up as engineers to improve processes in industry. So why is that, and I come to that in a minute, so different? And now it comes to the important thing, the most important slide, I would say. We thought, okay, this is not a program for making more scientific publications. This is a program to educate. So I had the feeling, and I always defined, because I'm the spokesperson, hey, this is a program where we make a new language, a common language. I said, this is the Esperanto of catalysis. And believe it or not, we started this before we got the cluster. We said we need a graduate school. And in the graduate school, you basically have, the assembling of all different characters and people in fields trying to contribute to the unification of catalysis, what I said about chemistry and biology. So we have every year scholarships, associate members, because not everybody was we associate. The academy does the same thing, right? You have fellows and you have associates. So we basically want to grow healthy in a way that we spread out, share ideas. Meanwhile, we have 140 PhD students. I can tell you 90% of them have a job before they finish. So we did some good selection. And half of them are going to academics after postdocs, spending some time somewhere else. And this is not a German club. This is an international forum. And what is also important, that's the difference to other graduate school, I would say. You also have graduate schools. They spend the first 3 months in the same room. They're not allowed to go to the lab and disappear and do what's the specialty stuff in the first place. They have education plan. They write their research proposal. They present the research proposals to themselves and to the audience, to the committee, and then they get a tick after that or say, you might have to modify that. That's the difference. So they get the smell to belonging to one family. And we have to do that, I think. I tell you what the outcome, science papers, you can look up this. I think it's real comfortable, all good. But what is more impressive to me is what is the spin-off. When the German taxpayer, by the way, this was over the year, we got every year about 7 million euros, about 48 groups all over the place in Berlin. We have 3 universities in Berlin, University Potsdam, 2 Max Planck Institutes, Helmholtz Center for Energy, and so on and so forth. So in total, 9 institutions, okay? So that is to ensure that this has a wide range. And we thought we need, as a spin-off, something which radiates and has a gravitation effect. And that was my idea. Hey, gravitation effect? There was this man, Albert Einstein, who discovered that gravitation is a different thing and makes us our universe, basically. So we thought we're gonna assemble all the activities in a meta structure, and we then were able to associate research as activities not belonging to catalysis on its own to this. So it's kind of a universal thing, right? To have the spirit and the common language thing. And we got an Einstein Center of Catalysis, which is an invitation to basically connect to, let's say, mathematicians, informatics people, genetics people, etc., right? So this is something which allowed us. And then, because we were successful and also in the educational way, personal development in industry is such a they said, okay, we need another generation of chemists. Who are the best people? So BASF asked us to perhaps establish together a campus. So we now have, since 2012, actually started a campus, BASF campus at the TU Berlin. And that is called the BASCAT, the BASF Catalysis Joint Lab. And existed, 2011, there was the bottle of champagne, but actually starting off this was 2012. It has a funding period ongoing, and the topic shifted from resources thing to green chemistry aspects. I don't want to go into details. And we have 3 directors, and one of the directors is paid by the BASF. So we have permanently someone from BASF on our campus, belonging to the team, which makes also a big difference. It's not only we want to have money, it's also we want to have the mindset change, and this is guaranteed by this. BASF has, in Germany, only 3 this kind of thing, and University of Heidelberg for homogeneous catalysis, KIT for battery research, and we are the heterogeneous campus, so to speak. Okay, new building, all facilities, so it's all in one. It's now, again, it's a unified complex where we do not only calculate, predict, but also synthesize and then test and then upscale, right? This is all in one building. And so it's all about how we see catalysis in the near future, making the gold standard in heterogeneous catalysis, which is basically the way of dealing with data. This is the gold in the future. If you know how to run, if you know how this works, what the parameters are which drive a reaction, you are in this. So it's, of course, again, a network in the catalysis and the data management world, which is basically here combined. Okay, I don't go into details, no worries. Gold standard, which means we're gonna follow a certain protocol. You see, again, it's not about publishing papers in the first place. It's about really to be sustainable, working with data which can be used later on. That's one of the drastic situations we are faced to. Many data in catalysis in the research are among different standards, so cannot be repeated and cannot be evaluated. So this is a huge problem. And here is the way we propose to change that. And in terms of using resources, the chairman said this, we cannot wait until new oil is coming off. So we're taking that what we get from nature, which is the sustainable chemistry stuff. We get renewables from the nature, and we're learning what these composites are and use that as chemists. And finally, make a point about spin-off 3. What is the future of the young people? Why should they study chemistry? To learn all the things and ending up in industry, which is an established industry, and had hard time to change. I recommend to go the third pathway. The third pathway is, why don't you just make a patent? You don't have to make a PhD actually for doing this, and trying to make your own business out of that. If you are keen in doing that, you don't have to go all through this, PhD, postdoc, somebody likes you or don't like you. So you said, okay, I have an idea, and I think even if it's a niche, I try, and there is support for this, so we start off this. So this is something we created. So I created a pre-startup center for green chemistry. It's called the Chemical Invention Factory. And we have among them already 65 startups which came off, and 14 are business-wise successful. They stay on their own feet. That's great. And the success rate is not very high, we know that. And the trick is to keep them on campus, to give them freedom, and to allow also industry and potential customers to join. We do not rent space, okay? This is something which is not allowed. I think this is an intellectual platform which enables this. So we got a new building. The new building is paid from the state of Berlin and from the Technische Universitat. We're talking about 9 million euros. At the time when we got the money, it was great. Then came this problem with the resources, pandemic and all stuff. So with that money, you would not get even half of the building. So fortunately, we could get more and stuff like that. But this is something which is ongoing, and this is a home for this third pathway. So what happens afterwards? Spin-off, we now go a step further. We make it more complex. Dealing with complexity is our business. We go for unifying systems in catalysis. So we would like to be like a cell, a biological cell, combining things where we have different steps of catalytic reactions which are interplaying and interconnected on time and space. And that's basically a long way to go. Most of the chemical reactions we perform in industry and on plant is we make a synthesis, we separate, we make another synthesis separate. As an outcome, square kilometers of a company is needed in order to produce something, right? What we eat, what we drink, what cosmetics we have is produced in this huge area. The vision is to shrink this, to basically scale this down on a level where basically everybody of us, even at home, you could produce something. I'm a big fan of this. The personalized way of synthesizing and making your life better. You don't have to rely on what big companies will sell you. I know that's very far away from reality. So this is I call this the Greenopolis. Okay, why not? The difference is in biology, everything is this is a nerve cell, and while I'm talking to you, millions of reactions are taking place in parallel. This is a chemical plant. They're producing 1 or 2 chemicals. You see the difference is tremendous. And we need to basically make a bridge here in understanding and scale this in a different way in order to be able to do this reaction networks, what we have in nature, evolutionary, and what we, by heart, produce in industry to have a chemical network, and it's still, you need that huge space and time to be able to do that, right? So the dimensions are really dramatic. So in our research program, we basically interconnect the various types of chemical reactions, of catalysis reactions, and we would like to learn from the feedback how we basically synchronize in time and space that this reaction can take place in one small entity, so to speak. And we're using the protocols of enzymes as well as chemical catalysts. Okay. And I like this animal here. We invented this animal. You see here, chemical catalysis, biological catalysis. So we get this conceptual movement, and then we thought, okay, we're gonna do this merge and focus on various topics. So we couple chemical reactions, chemical catalysis, biological catalysis, then the enzymes, chemical and biological, and then something which is extremely important these days is we're working with molecules which can be electronically accelerated with light or with electricity. So we do not need to rely on thermal chemistry. And that's called the catalysis of electronically activated molecules. What that is we will see in a second. Electronically activated molecules, we know this from photosynthesis. You have chlorophyll, and the chlorophyll gets a photon, and electrons are excited. Right? And this electron is then going away, and it produces a gradient, and you're producing proton-electron gradients, and they all go along a chain, and there, as an outcome, you're producing for CO2 and water, sugar, and oxygen. So this kind of process can also be applied, of course. Instead of activating chlorophyll, we can take chromophores, whatever you can do, produce in order to make the same, adapting this to the same processes for various reasons. We wrote an article in 2020 about this recycling thing. And Professor Mandel has pointed out CO2 is a big issue, and there are many people working on that. We have another focus here. The focus is, what about the other very energetic, important molecules which are not so easy to recycle? But that is to say, if you want to produce photovoltaic silicon from silicon dioxide, this has an enormous carbon footprint. So 1 ton silicon has a carbon footprint of about 6 tons CO2. So if you do that, if you say, oh, it's a solution, all good, we have photovoltaics, and all this problem is energy is solved. We don't have the idea how to make silicon without carbon, right? So therefore, it's a lot of chemical research needed. And this is also true for other elements, phosphorus, oxygen, sulfur, oxygen, which is associated to pollution problems, right? So we need to have catalysis in this. And the reason why it is so difficult is to reduce them is because of the bond energies. Here it's indicated, carbon-oxygen bond energy to pull apart the oxygen from the carbon. It's 799 kilojoule per mole. If you go to silicon, it's not far away from that. And if you go to phosphorus, the same thing, right? NO, same thing. So in other words, we should not stop at CO2 to look at this problem. We should go on in other types of molecules. And here's an example, a brief example. Phosphine oxide back to phosphine. You need 2 electrons, and the oxygen goes off as an oxide anion. On paper, very easy. In fact, this is, when you ask yourself, maybe why is that important and what is the relevance here? This is the way we still make vitamin A. As an example, there are many other reactions where phosphine is used. The phosphine is transformed into a so-called phosphorus ylate, and this makes a metathesis reaction, so they change the atoms. Phosphorus takes the oxygen, the carbon, so you're forming olefins. This is what the first way to make olefins. It was such a great discovery. Georg Wittig, 1979, he received the Nobel Prize for that. So this reaction is ongoing, so you're left with phosphine oxide. And the question is, first of all, to collect the phosphine oxide, and then to reduce it back to phosphorus. And this is a very messy business. So when you take a pill of vitamin A, you should recall this, right? Separating something in industry is substantial in terms of energy consumption. Most of the chemical reactions we invent in our laboratory will not make the step to industrial application because of the costs, for separation costs. So therefore, I bring this up here, the removal of phosphine oxide is a pain. And there are protocols, and people do that on a large scale. And if you want to reduce the phosphine oxide back to phosphine, you can use small molecule, high energy small molecules to do that, like silanes, boranes, and so on. This is done. Also, BASF did this, but then you're producing another type of waste you have to deal with after that, right? So you postpone the problem, basically. And chemical reduction, this is the newest patent from 1996. Look at this. They're using phosgene. Unbelievable. In order to make that guy here, and then using as a sacrificial reagent, so to speak, aluminum. They make an electrocatalytic reduction. So you're ending up with aluminum oxide. Also something you don't want, because this is also wasting resources, and it's very unlikely then to get this easily back. So this is the idea. Okay, excited state of phosphine oxide. We basically want to make electrolysis of phosphine oxide back to phosphorus. This is the idea. And of course, we were not the first one to tackle on this. All the protocols which are known, I show you here, are based on sacrificial reagents. So basically, you do the reduction, but you transfer the problem to another problem. You make waste. You're using aluminum mostly for that, so you have basically aluminum oxide production here. And one trick to accelerate, to facilitate the reduction is to lower the oxidation, phosphorus-oxygen bond order. It's a double bond, you see, to a single bond when you use a Lewis acid. So when this kisses the oxygen, the bond order reduces from 2 to 1, and then it's more feasible in electronic chemistry here to make this reduction process, but still high energy needed for that. Okay, this is the plan we had. We want to do all this, not only the phosphorus oxide reduction, but also the formation of the olefin in one part, in a consecutive manner, step by step. You can monitor, and you can basically do this with robots if you tell them when's time to stop and to inject in the next step. And the recycling of phosphine oxide for the Wittig olefination reaction. We start here, we reduce, we insert the compound which we're going to make, then the ylite we need to make, and then we make in the final step the olefination and make this. And all this should be tolerable to make the reduction process. So we make a circular chemical process here. Again, something which is not very advanced, not very developed these days. And the research questions I'm asking, I answer it. Otherwise, I wouldn't stand here to present that to you, right? So can we do? And the answer is yes. And there are a couple tricks. I said you have to lower the bond order. The problem is, why is it so difficult to reduce that electrochemically? The problem is that the phosphorus carbon bond energy is lower than the phosphorus oxygen double bond energy. So whatever you do, you excite electronically, you give energy, it's likely that the phosphorus carbon bond is broken. And this gives you a messy product mixture. You don't want that. Therefore, you need to basically activate. And what we use is an organic acid, Lewis acid, which again lowers the bond and the bond's order. But at the same time, when we do later on the reduction, we get a product. In that case, when we use methyl triflate, methyl cation, we get methanol. And for methanol, going back to a Lewis acid like methyl triflate is not a problem. So we again, this substrates we use here in activating can be recycled. Hey, that's cool. And when you submit such things to a journal, you'll see how the world is. An organic chemist gets this as a referee, says, of course, this is known. And electrochemist says, well, is that of relevance? Here we have a philosophical problem. You have to bring all this together. This is a showcase. It's just a starting point. Doesn't matter where, which journal, all this kind of. I want to encourage you. Give all this big name journals shit. I'm not frustrated, but look to solve a problem first. And all this honor stuff and all these kisses come afterwards, no worries. But I think we need to be really focused here. Now, if you do not apply this Lewis acid trick, you see, you gain not much energy if you add an electron in this, so exciting. But if you put this guy on here, the methyl oxide here, you gain 60 times more energy. Butch, you're gonna go through this, right? So, everybody can do this. This is a setup of an electrochemical cell, divided cell, and you can look at the phosphorus NMR spectroscopy when you have the phosphine oxide. This, of course, there is an electronic change. And then you do the electrochemical. This is a cyclovoltammogram. And you see here, dramatic lowering the energy you need in order to do that, 870 millivolts. And you do this, you're using a silver electrode. It's a silver cathode. This is where the electrons come from. In acetonitrile, not water, because otherwise you would produce hydrogen. Protons in water are also hungry. But you see here, this is we were not so happy, 93%. We got back the phosphine oxide and methanol. And the reason for that, I told you, is all molecules are lazy. You need to activate something that they fall apart. So we need a Lewis acid for doing that. And I show you why. So you go all the way along here, this electron comes in, and now if you have that species here, before it comes to this game here, you're gaining minus 50, you have another process where this bond can also be cleaved. So you have to ensure, in the presence of a Lewis acid, that this process goes in the right direction. And what we use as a Lewis acid was scandium triflate. This is a redox innocent Lewis acid. It sits there, it waits until it's ready to take off the meth oxide. Look at this, jump up to 79%. And we tried to find other stuff, but this was at the moment the best one. What are the drawbacks? This is almost stoichiometric amount. It's a high amount of scandium triflate. Although we can recycle, that's not what we wanted. And the other thing is silver electrode. You don't want to use a silver electrode. Are there alternatives? But before I come to this, I show you we really went all the way around because this was the first paper we published, we could basically make olefins from that in one pot. And all the products in the mixer doesn't harm. And then you have a filtration process after a certain time, and you have a certain concentration, and then you can basically work this up. So this is something which was really according to what we had in mind. Well, nice. And then we thought, okay, could we get rid of the silver thing and platinum? And then we said, okay, we use different types of Lewis acids, and this is one. We use tin triflate. Tin is cheap. And when we did this, we took the electrode, we used it and dipped it out. The platinum electrode turned black. And when we investigated what is on the electrode, it's elemental tin. I said, wait a minute, if elemental tin in this way, look at this, conversion rate, 98%, that's great. Ferritic efficiency, 79%, super. Can we do using tin instead of silver at all, and platinum? So we went in a shop, we bought stanniol full and used it, folded it as an electrode. Yeah, it worked. Because when you use tin foil, look at this, 92%. What it means is we do not need any additional Lewis acid. So the tin has a dual function. It is a metallic conductor for the electrodes. Electrons have to move. And it forms Lewis acidic sites. So they do the job that the meth oxide is carried away. That's great. We studied that, why is that, and so on. I skipped this. And now we are ready to do that, right? So George called me up and said, let's do it. Now we do this without this, silver, platinum, scandium stuff. So we make this kind of starting material, and then using the tin cathode, we were able to show that we can do that in reasonably also starting materials which are used in order to make pharmaceuticals. So of course, I'm not an organic chemist, but was pleased to see that colleagues said, hey, we're interested in that, why should we? This is also in the mindset of this systems in catalysis and this transfer of substance stuff and so on. And this is my proudest slide in this. So we make even natural products by that. And look at this guy here. We could make the starting material in 80% of vitamin A precursor using that protocol here. So all this was for us just perfect. What's the future? The electrons should come from renewable resources. So we do this reduction thing, and we oxidize an organic we can extract from nature, from wood, for example, and giving rise to starting materials which are used in other purposes. And look at that, we combined. You can do the oxidation of alcohols to aldehydes, and the electrons which are liberated here are used for making this reduction process here. So at the same time, we can combine. This is called paired electrolysis. You see here, we're scaling the complexity. We make circular things, and then. That's the future. And, everybody is invited to join this. And by the way, you don't need purified compounds, organic renewable compounds, to deliver electrons in here, making something which is perhaps of interest by its own. 12 principles of chemistry. Let's do it. Thank you so much.
What is your comment about the silicon oxide back to silane?
Right.
So that's one of the problem. Our boron always end up with BOB or
Right.
SI.
Yeah, that's a very good question.
So it's probably more difficult. I don't know actually. So is it possible to do that?
So if you look at the structure here, I told you we have the oxide, and when we basically lower the bond order, we add an Lewis acid, organic Lewis acid, we get this. This can be adapted by silicon compounds. Silicon has 4 electrons, tetrahedrally coordinate, but it has no charge. So you can basically take that same thing here if you have triphenyl silicon O methyl, oxide, siloxide, and trying to reduce that back to a silane. By what? Using a Lewis acid, where you have to add the Lewis acid again here to make a silicon cation, external addition. We're currently working on that. We have indication that works. The same thing is true for boranes. Now, if you want to do this with silica, SiO2, you need to produce soluble silicates, organosilicates are known, and to find the right Lewis acid to trigger that. I'm sure one is able to make elemental silicon nanoparticles in solution at reasonable conditions.
That will be really great.
You have a very large research group in Berlin University, where you are working. I'm just curious to know how many Humboldt Fellows you have hosted during your this research time, because there is a large number. India's total Humboldt Fellows,
Right.
chemistry shares a large number.
Right,
So
right.
that's why I'm asking this question.
Yeah, we do have, of course, guests from all over the world as Humboldt Fellows. In numbers, I personally had 9. And guess who was one of the... So this is one of the things to interconnect, that's right. But we also offer internships and guest professorships in the program. And but you're absolutely right. This is important. The attraction, exchange, and of course, the most important thing, the last slide, the the students who did the work, this is about, if you make a conference, the students should talk to each other. More space, more time, more experiments in ways to communicate. So this is on our side. If at a certain age, my age, I'm an old guy, so you need to, give the next generation the opportunity.